Hello everyone, welcome to today's tutorial. We are going to explore the Tower of Hanoi, a classic puzzle that perfectly demonstrates the recursive thinking in computer science. By the end of this video, you will understand the problem, know how to solve it step by step, understand the recursive approach with actual Java code, and learn the mathematical formula behind it. So let's start. First, let me show you what the Tower of Hanoi look like. I will explain more about the Hanoi Tower. So this one called a pig and this is a disk. I will name this as pig A, pig B and pig C. This is the source peg and this is auxiliary peg and this is the destination peg. So you can see there is three disks in different sizes. As you can notice, largest disk at the bottom and the smallest one on the top. So this is the arrangement. Here is the challenge. We have to move all the disks from peg A to peg C. It sounds really easy, no? But we have rules. We have three rules. We have to follow them. So first one is we can move only one disk at a time. We cannot move two disks together. That's wrong. The second one. Second one is never put a larger disk on the top of the smaller one. We cannot put the largest disk on the smallest one. That's wrong. So, the third rule, we have to use all the pegs. We cannot use only source peg and the destination peg. We have to use also helper peg. And it's impossible to solve this puzzle without using all the pegs. So now you all know about the rules. So let's solve this. Let me walk you through the complete solution for 3Ds. Our first move is the smallest one from peg A to peg C. And our second move is medium one from peg A to peg B. So our third move is the smallest one from peg C to peg B. And our fourth move is the largest one to peg C. And our fifth move is the smallest one again to peg A. And our sixth move is the medium one to peg C. And our final move, the seventh move is smallest one to peg C. So you can see we have followed all the rules and we solved this puzzle in 7th move. To further understanding, I will now show the animation of the Tower of Hanoi, this movement. I will explain the complete move sequence to understand the pattern behind it. So, first we move the small disk from peg A to peg C. Then we move medium disk from peg A to peg B. And again we move small disk from peg C to peg B. Fourth one is the key move. We move large disk from peg A to peg C. And again we move small disk from peg B to peg A. And we move medium disk from peg B to peg C. And the final move is we move small disk from peg A to peg C. Let's notice the pattern. In the first three moves, we changed the position of smaller disk to free the largest disk. And I said fourth move is the key move because we move largest disk directly to the target. And the final three steps we are doing for join the two small disks to the largest disk. So I am going to tell you the recursive approach of this puzzle. First, let's understand what is recursion is. Recursion means solving a problem by breaking it into smaller versions of the same problem instead of solving a big problem all at once. Let's look at the recursive algorithm to move any number of disks from source to target. Here we only use 3 disks. As you can remember, in the first 3 moves and the last 3 moves, we only move 2 disks. We ignore the largest disk. So no matter number of disks, we have to ignore largest disk in the first moves and the last moves. And there's a key move. There we move largest disk directly to the target. I have told you recursion means breaking problem into smaller pieces. So here you can see in this step 1 moving just 2 disks. So there we have smaller the problem. So in this step 2 it's just one simple move. And this step 3 again we moving only 2 disks. And now we can understand we broke 3 disk problem into 2 disk problems plus one simple move. I think now you have perfect idea of what is recursion means. So here is the visualization of recursion by recursion tree. Every problem has a base case. So let's talk about it. When we only have one disk, the solution is very simple because we can move it from source to the target directly. So then no recursion needed. Every recursive solution needs recursive case and the base case. In the recursive case, we break down the problem, and the base case, simplest version of that, stop the recursion. Let's talk about why recursion works here. The first one is self-similarity, and the second one is problem reduction, and the third one is base case exit. Do you know why we need the recursive thinking? Because we can practice to solve the simple case first and then focus about the bigger one and break it into the small pieces. It is good practice for everything we do. Let me quickly summarize the recursive solution. To move the disk, first we need to ignore the largest disk and the other ones moves to the auxiliary peg. And second one is move the largest disk to the target. That is the key point. And again ignore the largest one and move other disk from the auxiliary to target. And the base case is one disk just move directly. That one disk is the largest disk. Let's move on to the Java implementation. Here's the complete Java code of Tower of Hanoi. I will explain this by breaking it into this small code part. First, let's identify the parameters we have assigned. N for number of disks to move, and source is the starting peg, the source peg, peg A, and auxiliary is the helper peg, and it is peg B, and the target peg, the destination peg, peg C. The base case. Now we know what is the base case is. When we have one disk, we can move it directly to the target peg. So here this has assigned if n equal 1, system output print ln, move this one from source to target. That's what I said. Base case is if we have one disk, we can move it directly to the target peg. So this is what stops the recursion. Without this, recursion would never end. So we have to remember that always we have to use the base case when we do the recursion. So here is recursive step 1. Move number of disk minus 1 disk to auxiliary. So we use 3 disks. So number of disk minus 1 means 3 disks minus 1. As you can remember, we move 2 disks in the first 3 steps. We only moved 2 disks. That's what this says. Those disks are moved to the auxiliary peg. So here, target peg is used as a helper peg. This shows pegs are swapped their rules. This is first recursive code. Step 2 is the key move. Move the largest disk directly to the target peg. So, in the first steps, we clear the largest disk by removing the smallest disk. So here largest disk is free, we can move it directly to the target peg. This code part saying that this is the simple move without recursion. Recursion step 3 is move number of disk minus 1 disk to the target. The same step as first moves, but here we move that to the target peg. So here source peg is used as the helper peg. Here again pegs swap their roles. Here's the second recursive code. So here's the main method to run the program. Public static void main. We know that's the main method in Java program. So here's int number of disks assigned to 3. Since we are using 3 disks, we assign this number of disks 3. You can change if you're using any other number of disks. Here call Tower of Hanoi with peg ABC. So that's very simple Java implementation for Tower of Hanoi using 3 disks. So key programming insights are only 10 lines solve this complex puzzle. So you can see this is very simple code. Parameter swapping. Pegs are cleverly swap their roles. Source to auxiliary, auxiliary to target. So call stack. Each recursive call waits inner calls to complete. And here no loops needed. Pure recursion handles the all complexity. Turn complex problem to simple elegant solution. I will show the output of this code by running it on the online compiler. Let's see what happens. Here the output shows complete this movement for 3 disks. It's all about the code implementation. So let's find out the mathematical formula behind this puzzle. I will show you the pattern. If we are using 1 disk, there is 1 move. It is the base case. And we are using 2 disks, there is 3 moves. And we are using 3 disks, there is 7 moves. And we are using 4 disks, there is 15 moves. For 5 disks, there is 31 moves. So can you see a pattern in this? I know you exactly find out the pattern. Each number is double the previous and plus 1. So here is the formula to find the minimum number of moves. 2 to the power n disk minus 1. So when we are using 2 disks, 2 to the power 2 minus 1. That means 4 minus 1 equal 3. So let's verify the formula. For 3 disks, 2 to the power 3 minus 1. That means 8 minus 1, 7 moves. That's correct. For 4 disks, 2 to the power 4 minus 1, 16 minus 1, 15 moves. That's correct. For 5 disks, 2 to the power 5 minus 1, that means 32 minus 1, 31 moves. That's correct. So the formula is verified. So here I provided more details. Why does this formula work? You can get idea from this also. Here we can see exponential growth. The number double with each additional task. 3 disks, 7 moves, 5 disks, 31 moves, 10 disks, 1023 moves. For 20 disks, it is over 1 million moves. And for 64 days, lot of moves. I have added another Java implementation for move counter. I will run this code in the online compiler and show you the output. When we run it, we can see total moves are 7 and they given the formula prediction. And if we change the number of disks, we can see 31 moves are given here. Here we found out the mathematical formula behind this puzzle. Recap what we have learned about the Tower of Hanoi. First we learned the problem definition. 3 packs, 3 disks and move all from source to target. Next we learn about the rules. Rule number 1 is move one disk at a time. Rule number 2 is never put larger disk on the top of the smaller one. And rule number 3 is use all the pegs. Then we learn about the solution. After following clear pattern, we notice that 7 moves need for 3 disks. The other one we have learned is the recursive thinking. That's the important one. Break the NDisk problem into 2 and then plus 1 more. And I explained the Java implementation. Finally, we learned the formula behind this puzzle. The Tower of Hanoi proved us complex problems can have elegant recursive solutions. By breaking big problems into smaller identical pieces, we can solve what seemed impossible. If this video helped you to understand the Tower of Hanoi, recursion, Java implementation, please like and subscribe our channel. See you in the next video. Until then, happy learning.